welcome back, everyone, to the last session for today. It will be on modeling pollutant transport in soil and groundwater. So we just had the previous session of Gilles, who talked about modeling of pollutants to transport in plants. So I think this will be complementary to that. So this session will be hosted by two colleagues. So it's Ingeborg Joris and Chef Daams, who will present jointly this session. So once more, please feel free to add your questions in the chat. We will stop at some moments so that you have the time for questions. And yes, I think that's all I can say at this moment. So please, Ingeborg, the floor is yours.
Thank you, Christophe. And also from my side, welcome everyone to this session on modeling pollutant transport in soil and groundwater. What will we cover here? Well, we do the two parts. So first we start with modeling pollutant transport in soil, and then Jeff will continue with more focus on the groundwater, modeling pollutant transport in groundwater. If you look at the little scheme to the right, you can see that a contaminant that enters the soil at the surface will first travel apart through the unsaturated soil, and then in the groundwater, in the aquifer, which is the light green part here, it will travel further with the groundwater flow. Why do we want to model these processes? With a model, you can then predict the concentrations. So you can see where the pollutant will end up, what concentrations you can measure at a certain point after a certain time. First, the soil part. I will talk a bit about the processes that are involved in this movement of pollutants in the soil and the mathematical description, because a model basically is also based on the mathematical description of all these processes going on. And then I will talk about two applications. How can you apply these models in the context of soil management? That's in a risk assessment approach, where you can look when do you expect solutes to reach the groundwater and at what concentrations? So what is the risk of leaching of solutes to groundwater? And another application I will talk about more to the end is how can you use this type of calculations to derive safe values for reuse of soil and soil-like materials, so that you can do this in a safe way and the reuse of these materials will not impact your groundwater quality. But first, we dive a bit deeper in the processes. How do pollutants move in the soil? To the left, you can see a small scheme. So at the top, you have the soil zone. This is actually the arable zone. Below that, there is the deeper soil zone, which is still contains also air. So it's the unsaturated zone. And below you have the groundwater or the aquifer. That's the zone which is completely, where all the pores are completely filled up with water. So your solutes will move primarily vertically through the soil to the groundwater table. The main driving force, of course, is the water infiltrating from the top, your rainfall, the rainfall that's infiltrating. So your movement is also mainly vertical. It's also mainly downward, but of course, if you have a moving groundwater table, if the groundwater table also rises, then you also have upward movement of the solutes. That's also possible. So this is the driving force. This determines how the solutes move in the unsaturated zone. What happens? Well, a lot can happen to the solutes or the chemicals when they are during this transport. They are subject to the convective transport. That's actually moving with the infiltrating water. But there's also other processes that influence the concentration. Sorption to the solid phase, volatilization, where they go into the soil air, and dispersion or diffusion processes. And degradation is also possible. The concentrations you will find, the concentrations reaching the groundwater, depend a lot on the substance properties, because the substance properties will determine if you have volatilization, but also if decay is possible. For instance, heavy metals are not subject to decay, and also on the soil properties. So it's the combination of the two that will determine how much of your solute will reach the groundwater or how much you can find in the soil layer. Just let me move that, okay. So to have a better grip on this, we start with the phase distribution. This depends also very much on your solute. Is your solute more likely to be found in the water phase of the soil, in the air phase, if it's a volatile solute or contaminant, or on the solid phase? Usually we talk about these three phases when we talk about soil. You have the air, the solid, and the water. I think in the previous sessions, you probably already had a lot of information on this. As a rule of thumb, we say that the soil consists about 50% of solid material, and the other half consists of pores that can be filled with water or with air. In some cases, it gets a bit more complicated and you have 4 phases. Then you don't only have the water, air, and solid phase, but you can also have a non-aqueous phase liquid. This can be oil or gasoline. These are liquids that are not prone to dissolve in the water, and they're present in such a high concentration that they form a 4th phase in the soil. A small example of a very complex distribution for PFAS. It's just an example. You can see here in the circle is your soil with the solid phase that are the gray moon rock-like particles here. You have an air phase, you have a water phase in blue, and there's also a NAPL phase, a non-aqueous phase liquid, which is present as a 4th phase. And the PFAS will be just distributed among these 4 phases, and it will have a high tendency to go in the NAPL phase and also to go into the interface between the water and the air. So sometimes this can get quite complex. It's not always like this. If you have a heavy metal, this will primarily be distributed among the solid phase and the water phase. Why do we want to know where the solute is? Because in the different phases, there will be different processes acting on the solute. If you have a concentration in the gas phase, it will be subject to diffusion. So it can move in the gas phase driven by differences in concentration at different locations. If it's in the solid phase, it can undergo chemical reactions. It can also be diffused in aggregates of solids, so in aggregates of small particles. And in the water phase, it's usually the most mobile because it's in the water phase that solutes will leach to the groundwater. And there, your concentrations are subject to dispersion and convection. And from the water phase, you can have leaching to the groundwater. Of course, you also have the biological phase, and you probably heard earlier this afternoon. It's very important, of course, if your solute, in which phase your solute is, because it's usually only in the water phase that it's available for plants, for example, to take up the solute. So now we go to some mathematical description of what I have been saying. We're not going deep into this, but of course, if you want to take the step to modeling, in modeling, all these processes are described in equations. So this is an equation that describes how your chemical partitions between the different phases. We assume here that you have a soil that consists of a solid phase, a liquid phase, and a gas phase. So 3 phases, the most classical or natural situation. Your total concentration is made up of the sum of your concentration in the solid phase. This is here called Ca. Your concentration in the liquid phase, Cl, and the concentration in the gas phase, Cg. And each of these concentrations in the separate phases are then multiplied by the volume fraction that the phase takes up. So as I said, as a rule of thumb, your soil is made up of 50% solid, 25% liquid, and 25% air. But that's very generic. Of course, in reality, it's a very dynamic system. So your volumetric water content and your volumetric air content constantly change in the soil. Okay, so we have our distribution over the different phases. And what are now the relations or the processes that take place? If we look at the liquid-solid distribution, so how will the solute be distributed over the solid phase and the liquid phase? This is called sorption. So sorption is the tendency for a solute to go onto the solid phase. And this is typically described by sorption isotherms. So here you have some examples. So each of these lines is a sorption isotherm. And what it says is over the range of concentrations, this is the concentration in the liquid phase, it tells you what's the corresponding concentration in the solid phase. So this is the liquid-solid distribution. The isotherms are usually determined experimentally, so they're empirical relations, and they can be described by different types of equations. So in the most simple case, you have a linear isotherm. That's the red one. It says that the proportion or the ratio of your concentration in the liquid phase and in the solid phase is always constant. So it's one value, which is called the Kd value. So for a certain soil and a certain solute, you have one value, the Kd, that says how the solute will partition over the solid phase and the liquid phase. Often, this is not what the experimental data say. Often you have a bit of a different type of curve. And then you can have, for instance, the Freundlich isotherm to describe the sorption behavior, which is the green one. That says that your concentration in the solid phase is a factor, also the Kd, times the concentration in the liquid phase to an exponent. So then you have two values, two numbers that describe your sorption behavior. And a bit more complex even is then the Langmuir isotherm that actually describes the behavior that you have sorption from the liquid phase onto the solid phase up to a certain point where your sites, your sorption sites are fully occupied and you get a flat line. That's also a behavior that can be observed when you do experiments to determine the sorption, and there is equations to describe this type of behavior. But just some examples to make it a bit more concrete. So desorption is usually an experimental determination. Here to the left, you can see some points for 3 different soils. So the symbols are 3 different soils. And you can see that for each soil, if you make a graph of the liquid concentration and the concentration on the solid, the absorbed concentration for cadmium in this case, that you really nicely see linear isotherms. So in this case, the linear isotherm is a very good representation of what you see here. And this simple equation where you just say concentration on the solid is Kd times the concentration in the liquid is actually perfectly working for cadmium in these soils. So if you have an experiment and you can get this Kd value, you can use it in your calculations to describe sorption. This is in Australian soils. It's from an article. To the right, this is a study that is performed on a range of soils in Flanders. You can see a bit more a range of KDs. So here also, if you assume this linear sorption and you have a KD value that describes the sorption, for a number of soils, these experiments were done. And the relation between the KD and other soil parameters was established. So now for Flemish soils, if we know the basic soil properties, we have a good idea of the KD value for different metals. For instance, if we look here also at cadmium, which is the second one in the table, you can see that if you know the pH of the soil, you can calculate a log Kd value, and from that, the Kd value that describes sorption of cadmium in this soil. So of course, if you have this type of regression equations, it means that you don't always have to do these experiments again, of course, because that's is quite an effort and you don't want to do a sorption experiment on each soil. So we have relations that describe the sorption, and we have, in some cases, there's a lot more literature, we have estimations of these Kd value based on soil properties. The examples I gave were for metals. Of course, you also have a lot of organic compounds in the soil. This can be PAHs or other components. These organic compounds often have a tendency to sorb on the organic matter. So more on the organic matter of the soil than on the mineral particles. Often they are they don't have a strong tendency to go to these charged mineral particles, because these mineral particles have a layer of water around them. So the organics tend to sorb on organic matter. If we then look what this means for describing sorption in equations, as we did before, you can see that for a lot of these compounds, like PCBs, PAHs, or pesticides, the Kd is a function of the fraction of organic carbon in the soil. And the equation describing it is that the Kd is a KOC factor times the fraction organic carbon in the soil. What this means is that you have a compound property, the KOC, that describes this tendency to go onto the organic matter phase of the soil. And if you then know how much organic matter you have in the soil, so this is actually the fraction of organic carbon that you can measure in the soil, you have a Kd values. So you know how strong the sorption is. So this Kd depends on the KOC, a compound property, which you can find, you can do experiments, but you can find in the literature. There are many reviews of KOC values for all kinds of properties, and the fraction organic compound, so the soil property. And here you can see some of these KOC values. As I said, you can find them, you can look them up. So it's not something you need to determine experimentally. Of course, it's always a possibility, but that's a lot of effort. You can find these KOC values, and here these are actually a range of organic compounds. The first ones are pesticides, and you can see that it's very different, of course, for different types of compounds. For instance, for DDT, the pesticides that was used a lot decades ago, a long time ago by now, you can see that it has a very high KOC value. This is why it sticks very hard to the soil. If you have a high KOC value, you have a high absorption, so it sticks to the soil. If you then look, for instance, at this bromacil, which is another pesticide, it only has a KOC of 32, so it doesn't have a high tendency to stick to the soil, and it will be very mobile. And these types of compounds have a high risk of leaching to the groundwater because they tend to stay in the water phase and they are washed out to the groundwater. And you can see that the range covers different orders of magnitudes. So yeah, from the 10,000 to 32 or 50 for the xylene, naphthalene also is quite mobile. So there was sorption, which is a very important process in determining movement of solutes, because it determines if your solute rather sticks to the soil or is very mobile in the water. So it's very important. You also have a similar type of distribution coefficient to describe the liquid gas distribution. So this tells you if your solute has the tendency to go into the air phase. And that's also important to know because if it goes into the air phase and you have a shallow soil, you're close to the surface, it can also come out of the soil. So you can have vapor intrusion in buildings, for instance, if you have a building there. So it's very, it's also crucial to know. And for the liquid gas distribution, we have the Henry coefficient, we call it, or the Henry coefficient. That's from Henry's law, which describes the equilibrium between the concentration in the gas phase, Cg, and the concentration in the liquid phase, Cl. This is also a value which is available from literature and something you can get for your organic compounds, because metals typically are not volatile except mercury, but all the other ones, they are not volatile. But for organic compounds, you have a big range going from, for example, for benzene, it's only 0.17. So this is a very high value. This means that benzene has a high tendency to go into the soil air, the soil gas phase. But then like bromacil, we saw earlier, it's mobile in the water phase. It will not go into the gas phase. It has a very low Hartley coefficient. Also here, we have several orders of magnitudes, because here it's 10 to the minus 8, and here it's 10 to the minus 1. So it's very different for the different organic compounds, and it's something crucial to know if you want to know where you are likely to find your solute in the soil. Okay, the next one is then degradation. Also not relevant for heavy metals because they are not subject to degradation. They can sorb to the soil, but they are not subject to decay, so they will not disappear. But organic compounds can and usually are subject to degradation. The mathematical equation to describe that, or that is usually applied in models, because we have different types of reactions, but usually we assume a first order reaction for degradation. This means that the rate of degradation actually depends on your concentration, but what it looks like in if you look at it as a function of time, you can see that your initial concentration that is present will, of course, go down with time. And this follows then a first order kinetics. This is an example for atrazine. And you can see that if you would start from a concentration 1, well, it's here a relative concentration. So your initial concentration is 1. This is your CT0. That it will go down to 0.5, so to half of the initial value after approximately 70 days. And this is the evolution of concentration we expect if we assume this first order reaction, which is usually a very good approximation of what we observe. So this DT50 is the key parameter here. The DT50 is the time it takes to go from the initial concentration to half of your initial concentration. So this is called the half-life. You go from the initial value to half the value. And this time is then the DT50, or the half-life. I also listed for some organic compounds, the DT50. And also, this is the rate of degradation, this mu c, but this is the DT50, the half-life, which is also a bit easier or more intuitive to understand. You can see for DDT, which we saw that it has a very high KOC value, so it sticks very strongly to the soil. We can also see here that it almost doesn't degrade. It takes 6,200 days to go from the initial value to half of the concentration. So this is, we can call this persistent. A DDT is a persistent and non-mobile substance. So this means that it stays in the environment and it stays in the soil. It doesn't go to the water phase. It stays in the soil almost forever. This you can tell from the constants that we had. Here are other examples of other pesticides. It's a list of pesticides because they're also quite well studied. Degradation behavior is quite well studied because it's very important to know before you are allowed to use it. And for these pesticides, it's a lot lower, so a lot shorter. So for isoproteron, for example, which is a herbicide used in corn, it's only 12 days. So after 12 days, your concentration is halved. 13 days for bentazone, and these are some other examples. So this is a third very important parameter for your substance. We already had the KOC or the KD, the Henry coefficient, and now we also have the half-life. Then some more processes. Now we talked a lot about the partitioning. So where will your solute be? And how long will it stay there? Is it subject to decay or not? Diffusion and dispersion are really processes during the transport of your solute through the soil. The dispersion, hydrodynamic dispersion, is very much related to the pores present in the soil. So because your soil consists of a solid phase with all kinds of pores in between, you will have the effect that your solutes will move at different speeds. So depending on the pore size, if you look here to the left, we have some factors why we speak about this dispersion. Depending on the pore size, your solute can pass very slowly if it's very narrow, or very fast if it's a bigger pore and it's a highway. So then it goes fast. If it's a very narrow pore, it goes very slow. Also, your solute will have to move between these particles. So sometimes it can have a very long path. Sometimes it's very easy, it's quick and easy, and there's a short path. And within these pores, you also have a different friction. If your solute is right in the middle, it will go fast. If it's closer to the particles, it will have some friction and it's slow. So you see that if you start with a bunch of solutes at start, they will encounter very different circumstances, and some will go fast, some will take a long time to go through the soil. If we then now look to the right, how we can depict this, here we say, okay, this is the start line. You have a lot of solutes ready to go through the soil. Then they start, some get even stuck here. They're very close to the solid. Some can go right through. If we then look at the finish, so let's say that here in the right, there's the finish, you can see that it's all spread out. Some arrive very fast, some arrive very, very slow, and a lot of them are in the middle. And this is called the dispersion. So you can start with solutes at the same time, but they will get spread out during the transport because you have this porous medium, which causes all kinds of complexities for the solutes to pass. So dispersion is spreading in concentrations. Another process that occurs is that if you have then different concentrations in the soil, yeah, you can see also because of the dispersion, you will have zones with higher and lower concentrations, sometimes close to each other, but you have differences in concentration, and then you can get diffusion, because differences in concentration will cause solutes to go from zones with high concentration to low concentration. So it's an extra push. So you also have diffusion. These two processes can be described similarly mathematically. So usually they are combined. So we speak about effective dispersion, and that combines all of this. The hydrodynamic dispersion, diffusion, it's all lumped into effective dispersion. And now we come to the full description. So please don't get frightened by the long equation, because it's not, you're not supposed to really remember this, but this is how the processes are combined in one mathematical process description. So all the things I talked about before are here combined. So for the transport, we have this first equation that describes conservation of mass. Actually, what it says, it's not, it may look a bit complex, but actually it's not so complex. It says that if you have a certain volume of soil, the change in concentration in this small volume can be, yeah, it's what's coming in minus what's going out, both in the gas phase and in the liquid phase, minus what's degraded. So this is just describing the conservation of mass in a small volume. You have the difference of what comes in and goes out, and then what gets degraded inside this volume. This has to even out. So the changes in concentration are the sum of these fluxes in and out and what's degraded. If we fill in all our processes we talked about in this conservation of mass equation, we get the convection dispersion equation for chemical transports in soils. Here it's in 1 dimension. You can also have it in 3 dimensions. So this is the basic equation that describes all the transport processes that we discussed combined in one equation. So you can see here, yeah, it's the change in concentration. The concentration is made up by concentration in the solid phase, liquid phase, and gas phase. This is determined by what comes in and goes out through diffusion in the gas phase, through convection in the liquid phase. Convection is just the infiltrating water, so moving with the water. Dispersion and diffusion, the spreading of the concentrations, and degradation. These are all the processes that can take place. They don't always take place. But it's quite a big equation, of course. It's a partial differential equation, so it's not so easy to solve this. So this is not something that you solve by hand, but this is behind the models for transport of chemicals in soils. And then an example, well, it's an example calculation. It's not calculated by hand. It's calculated with a software code, but just to get a feel of the impact of the different processes we described on what you see in the concentrations reaching the groundwater. So what do we have? We have an experiment. It's a hypothetical experiment. You have a column of soil. You have water going from the top to the bottom. And at the top, a pulse solute input is given. This means that you release at a very short time, you release solutes into the column. So it's one very small time period with inputs into this column where water is flowing. And what do we see then at the outflow? And how does this look if we if some of the processes are more or less important? And that's what we see at the bottom. So if we have our standard parameters that are listed here at the sides. So let's say you have a column, it's 50 centimeters of length. The velocity of the water is 2 centimeters per hour. There is an effective dispersion coefficient of 2 square centimeters per hour. Retardation is 1. This means that your solute just moves with the water and there's no degradation. With these numbers, you get the dark blue curve, for example, here. And in this left plot, we say, okay, let's turn up the dispersion. So if you have a higher dispersion coefficient, what happens? You see, you have the peak of concentration coming out. The dark blue is the standard scenario. If you have increasing dispersion, this means that your concentrations will be more spread out. So you can see the green one with a dispersion coefficient of 3, or the light blue dispersion coefficient of 10. So this means that the maximum concentration you find at the bottom of the column gets lower, you have more spreading out, and you also have a longer period of solutes arriving. So it gets lower and wider. That's what dispersion does. What would happen if we increase the sorption? So this is here depicted by this retardation factor R, which is related to the KD. So the standard scenario, this is actually the same dark blue curve. This has no sorption, basically. If we say, okay, our solute does sorb to the soil, and we increase the retardation to 2 or 3, then you see this has a very strong effect on the maximum concentration you will find, and also just on the amount of solute that you will find at the bottom of the column. So sorption causes the solute to stick to the soil, so you will find less in the water below. Lower maximum concentrations and just less solute. And the third example is then what happens if we have degradation in the column. So the dark blue is exactly the same dark blue curve as before. If we have no degradation, if there is degradation, you just see that the concentrations go down. There's no effect on the timing, so it doesn't mean that the solute will spread out more or go slower, but there's just less because the rest is degraded in the column. Yeah, and then this is to end the part on the processes. We saw this convection dispersion equation. It's a very complex partial differential equation. So how do we deal with it? In some cases, it can be solved. It can be solved. It means you have analytical solutions. That's a direct solution of the equation. But this is only in certain cases, and if you don't have under very, very strict boundary conditions. But it exists. So you have analytical solutions, and there are software packages which are very robust, very fast, that can do this for you. And here I've given some examples. In most cases, the convection dispersion equation is solved numerically. And then you have the software packages, so the models. If you have a model that simulates solute transport in soil, it's a numerical model that uses mathematical techniques to approach or to converge to the right solution. And examples of these are for hydrous 1D or 2D or 3D. So 1D means that you look at one dimension. So your solute transport follows a line vertically. Can also be other directions, but usually vertically. 2D or 3D means that you really describe a cross-section through the soil, or a 3D soil column. So these packages exist. Hydrous 1D is free. Other examples like Pearl and Macro that more focus on pesticide transport, but are also solute transport models in soil, are also freely available. So the models exist to be used and to model solute transport in soil. So you don't have to figure out the processes yourself, but hopefully now you do know what the parameters that the models ask, what they stand for, or what they mean. Yeah, so next I will describe two applications of this type of modeling more practically in the soil management context. But maybe we should stop for questions now, Christophe, or should I continue?
No, that's okay, Ingeborg. Indeed. Thank you for this already very comprehensive overview. I always thought that modeling was difficult, but as you explained it, it sounds very easy.
It's very easy. It's fun.
Yeah, it's fun, yes. I did not receive any questions, but I think you were very clear and you explained very well. So I think you can continue with the examples that you have prepared.
Okay. I will, try to be a bit briefer maybe on the examples. So Chef also has some time left. But these are applications of these models in risk assessment approaches. So I will, as we saw, solutes leaching from soils that contain contaminants, they can pose a risk for groundwater quality because the solutes will eventually reach the groundwater. And in Flanders, you have had some presentations on the legal framework. There are limit values or standards for soil, but they don't really take into account this risk. They are based on ecotox risk assessments, on exposure risk for humans, but not really on the risk of leaching to groundwater. So to fill that gap, we made an approach to assess this risk. And it's a tiered approach. I will explain here. A tiered approach is something that is often applied in all types of risk assessment. It means that you can do the risk assessment with different levels of complexity. If you don't have a lot of data, you can do a tier 1 approach. You don't need a lot of data, it's very basic, and you get a very conservative risk assessment. It means that the risk will be conservative, so it will be assessed as to the high side. Same, if you don't know it, you go a bit high. But if you have a situation that passes even your tier 1 assessment, you know, okay, here's no risk. If you have a little bit more time, a little bit more data, you can do a tier 2 assessment. There you get a more realistic risk assessment, but it takes a bit more effort. And if you go for a full impact assessment, that takes more effort, but it gives you an even more realistic approach. How does it look like for our risk assessment? The first tier is a calculation of a screening value. You don't need a lot of data for this, and it can already tell you if there's no risk there, then you're safe. The second tier is a source path receptor analysis, where you will use a model, but it's an analytical model, so it's not too complex. And the last tier is an impact analysis with specific numerical models. What does it mean, this site-specific screening value? It means that for a certain site, you assess, and a certain solute, of course, you assess what soil type is present here, how vulnerable is my groundwater, and just based on this, it's possible to calculate a screening value. You assume that your solute is partitioned over your solid water air phase, and the concentration of the liquid phase is in contact with the groundwater. Now you just assume, okay, this is in contact with the groundwater. The only thing that happens is that you go from the soil into a large volume of groundwater, so you have dilution. So that's all the processes: chemical partitioning and dilution. You then calculate the screening value as the concentration that you want to allow in groundwater, your quality criterion. Calculate it back. So you distract the dilution and you convert it to the total concentration. But it's very, the only things you take into account are partitioning and dilution. What do you need then? Absorption coefficient, a KD, and an HRE coefficient, of course, for the volatilization. And for the groundwater, you can assess this dilution factor if you know mainly the hydrogeology of the site. The groundwater, the phreatic groundwater there, what's the hydraulic gradient, what's the conductivity, and how thick is my layer. And for Flanders, in the frame of this risk assessment, we made a map of these dilution factors. I just show it very briefly here. But then you can see that you have zones here in the east where you can have quite high dilution. It goes up to almost 10 because you have there a very thick layer of groundwater that's flowing very fast. So everything leaching in that type of groundwater will be diluted very fast. So you can divide your concentrations by 10. On the other hand, in the west, you have very little groundwater. It's not flowing very fast. There you hardly have any dilution. But with this map and some assessment of your KD values, you can already do the risk assessment. So then you have a site, you measure your soil concentrations, and you can see, are they above the screening values? If this is not the case, so your screening values are not exceeded, then you have no risk. If you do have exceedance of the screening values, then you might have a risk. You're not on the safe side, so you should continue your assessment and you can go to tier 2. Then the source path receptor analysis. We have a very simple transport model developed for that, but that can tell you already how much your concentration will diminish when your solute moves through the soil. So if you have a contamination very close to the surface and your groundwater is very deep, then you will have a diminishing of the concentration. All the processes happening in the soil, your sorption, your dispersion, will cause a lowering of the concentration to your groundwater. And in the simple transport model, you can take this into account. We have just two typical scenarios then, and we only consider 1D transport. What's extra or new in this tier is that you have to define your receptor. So you have to say, okay, in Flanders, we decided that if you have a contamination in the soil, but there's no contamination in the groundwater yet, then your groundwater should be the receptor. So that's the thing you want to protect. If you have a contamination both in the groundwater and in the soil already, then your receptor is, can be, for instance, the limit of your parcel or some drinking water well or a small river downstream in the groundwater. Okay, so then compared to the first tier, what additional data do you need? Well, you have your source path receptor, so you have to choose your receptor and you have to know where the contamination is in your soil. So is it at the top? Is it already very deep? If it's in the groundwater, also how large is your plume already? And you can enter now also decay, so half-life values. Now you calculate your concentrations at the receptor with the simple transport model, and then you can see, are they above your groundwater quality criterion? If that's not the case, there's no risk, so you're safe. If that's the case, your risk can still not be excluded, and you can either decide that there is a risk, or you can proceed to a full impact analysis. I don't want to go too deep into this because I know time is limited, but then you can use numerical models and you can also simulate very dynamical boundary conditions, which are much more realistic for a soil. And there's just one example, but I'll just stick to the figures. This is an example where you have a soil contamination of PCE. So PCE is perchloroethylene, which is degraded in a chain reaction into different daughter products. And the last one is vinyl chloride, which is actually even more toxic than the mother product. So it's actually quite important if you do a risk assessment to know the whole chain of reactions from PCE to vinyl chloride. And that's something that a simple analytical model cannot do. So then you need more complex tools. And here you can see how the PCE, if you only look at the left side, you see that it leaches down to the groundwater, but it also disappears. So you can think, okay, that's good news. My contamination after 4,000 days is practically gone. But at the same time, you see that the daughter product, which is quite toxic, is appearing. And after 10,000 days, you have quite a plume of vinyl chloride. So to do this complete impact assessment where you see the different products, you need more complex models than a simple analytical model. This is done in hydrous, for instance. So this is something that's done in hydrous. And just to finish, another very brief example of how these models are applied in soil management. We also use them to derive safe values for the reuse of soil and soil-like materials. So we have legal limits for the reuse of soil for all kinds of purposes. That's the free reuse of soil, or in construction works. That's a specific reuse. These are based partially on risk-based limit values, which are calculated with models, transport models in soil for specified application scenarios where safe concentrations in soil and groundwater are to be protected. So to get to these reuse values, first you determine which are the safe concentrations in soil and groundwater that you don't want to exceed. And then in these standard application scenarios, the model is used and you can calculate the maximum value that's allowed not to exceed these safe concentrations. And from this, then legal limits for the reuse of soil are determined. These are then the scenarios, the application scenarios that are fixed. So you have a typical reuse scenario, and that is used for your calculations. So here it's a reuse of soil on top of a soil, an unsaturated soil of 1 meter and a phreatic layer below. There's also an application scenario for reuse directly in the groundwater. And these different scenarios, each different scenario will give you a maximum allowed concentration. So you have a maximum allowed concentration here not to exceed the concentration in soil. We say, okay, top 30 centimeters after 100 meter. That's the concentration that cannot exceed the safe value. You have another maximum allowed concentration not to exceed the groundwater quality value. If you have these risk-based values, of course, they have to fit into the soil decree because they're part of the soil decree. They have a legal status. Then you have to fit them between the background value and the lowest, the strictest soil sanitation value. But that's maybe not so. And this is then the very last. So for instance, for arsenic, we have these 3 typical application scenarios. For each of these, we can determine with the simple transport model, what's the maximum allowed concentration. So that's 11 directly in groundwater, 23 on for an average soil, or 67 for a sensitive soil. So these are just 3 application scenarios. Then we know that the natural background, as it's stated in the soil decree, is 16. So our reuse value should be at least 32, at least 2 times this 16. And it should be a bit lower than the strictest soil sanitation value, because otherwise we are speaking about soil contaminations. And here we are looking for free reuse values to use all over the country, not only in contaminated soil zones. So based on this, the value is put at 60% of the strictest value. You can see that this is a safe value, looking at our risk-based limit values, and it fits into the soil decree. This evaluation or assessment then is a bit different for different different compounds. So I've just given 3 examples here. So this is another application of the transport calculations in soil to feed into the soil decree actually. This is just for your reference, of course. And then this is the end of part 1.
Okay, thank you very much, Ingeborg. It's also good that you showed the last application on the reuse of soil, as I think also in our previous, there was a lot of discussion on craters. And I think indeed filling craters with other soil and how to calculate maybe then leaching is also something that's of interest. So I think this last part was definitely also good to mention.
Yeah. If there should be questions on that later on, that's also still okay. Yeah? I mean, if there's specific.
Yeah, I see already one question, Ingeborg. Are there any models to model lateral movement of pollutants?
There are. Usually in the upper soil, in the unsaturated zone, the movement is downwards. So it's very typical to just have 1D vertical movement. But like the Hydrus 1D, you can move, you can assume any direction. So you can also assume lateral transport, or you can apply, like in the example, but with the PCE, you can make a 2D model that it can move both laterally and downwards, that you describe a two-dimensional transport. So that's, yeah, it's perfectly possible. It all exists.
Okay. I hope that answered the question of Alexander. Is there any other comments or?
I'll ask a quick question. You mentioned when we were doing leaching potential for groundwater, there was the requirement of having a groundwater receptor in the vicinity. Does the Belgian regulation account for like future potential groundwater use? I'm just thinking from an example here from the Canadian context, we used to have, for groundwater standards to apply, you had to be within a certain distance of a groundwater receptor. But then they changed that to say, they apply everywhere in the country because potentially someone could want to install a groundwater receptor in the future. And now you have soil or groundwater that is higher than the standard. Is that future? How is that taken into account, or?
It is implicitly. So you have the two different approaches. The part on the risk assessment where you choose a receptor in, that's the case of contaminated soil. So you really have a situation of contaminated soil, and then within this dossier or this case, you have to define yourself. Okay, this is my receptor and this is my maximum admissible value. But the last application for the reuse of soil, these standards, then it's everywhere. So actually we say that everywhere where you reuse soil, the groundwater should be at still drinking water quality. That's now how the Belgian law stated. So it's a different type that's more diffuse, and then it's also future use.
Okay, thank you, Ingeborg. I think we can move on to the last part of the session, to Chef. So first of all, Ingeborg, thank you once again for this very nice presentation. And Chef, if you can or try to share your screen at first.
Yes, let me try that.
Yeah.
So no, we just continue? Or?
Yeah.
Okay.
Or did you had other plans?
No, for me it's fine. The time is limited, of course, but
yeah.
Is this the correct screen?
No. I think we now see your all your slides.
Ingeborg, you found the perfect button for this, huh?
You need to switch to the slideshow. It's still in editing mode.
Yeah.
Okay. It's a bit too big now.
You're still not in really presenting. I mean,
presenting
we don't.
No, I'm still trying to get it.
No problem. Yes. Yeah. That's how it.
That's the correct one.
Yeah, that's we see now perfect your presentation mode, so that's working fine. I don't know if you have a mouse or something that you want to point out in one of your slides. Yeah, it's working as well. Okay, then Jeff, we're all settled, so please go on.
So my part will be on the pollutant transport in the groundwater system. So Ingeborg explained to you how the pollutants are traveled from the terrain surface to the in this case the top of the aquifer, so the water table. And in my part, I'm going to explain how the pollutant will be transported or can be transported in the groundwater system itself. Time is a bit short, so I'm definitely not going to be able to to describe all my slides in detail. So I will do some parts really quick, but you can use the slides as a reference, and if you have want to have more detail further on. So what I was thinking is to give a short introduction on groundwater hydrology. So that there I will really go very fast. Maybe you know most of it, or there have also been parts that were discussed in the previous presentations. I know. Then there is a basic principle on the groundwater modeling, the flow modeling, and then on the transport modeling. And in the end, I have some practical guidelines. And I think maybe it's most interested to spend some time on that part. So basic principles on the groundwater. I assume you know by now that you have the unsaturated zone, the saturated zone, with the groundwater table being the divide. The groundwater system is characterized by hydrogeological characteristics, and similarly as the unsaturated zone, as Ingeborg described. Also, the porosity plays a quite big role in the transport of pollutants. You have the storativity characteristics and the hydraulic conductivity that determines your transport. So the hydrogeological layers, and you have unconfined layers which are in contact with your land surface and your river system. You have sometimes also aquithards, so systems that are contain mostly of or clay or peat that are less permeable and where the water is kind of stopped. And then sometimes underneath these aquithards you have confined aquifers that are not in contact with the land surface. It's very interesting, of course, if you have a lot of detail on how the hydrogeology of your study area looks. In Flanders, we are very fortunate to have a very good data sets on our hydrogeological system. So this is, for example, on a cross section in Flanders, where you can see all the aquifers with full filling, and then the aquithards with this white stripes in between. So you have the full overview with information on how deep they are at each location in Flanders. I tried to look up some Ukrainian data, and this is one map I found. So I noticed here you have aquifer systems in Ukraine that are also very productive, with containing quite porous aquifers where a lot of water is stored. So these are parts. These bluish parts are definitely parts where you could have pollutants reaching quite easily also your aquifer system. Then on the basic principles, porosity, it has been described. So the pore volumes, you have porosity by itself, but also the effective porosity that mainly determines then how your water can be transported in the subsurface. So the storativity is a measure of how much water can be stored in the aquifer system, and its effect subdivided by specific yield, which is most determined in the unconfined aquifer system, and storativity term, which determines your storativity in the confined aquifer system. Then the transport is generally regulated by the hydraulic conductivity of your aquifer system. I think in the presentation of my colleague Jan Bransers, he also mentioned Darcy's law is very often used in groundwater transport. So the hydraulic conductivity is in fact determining, together with the difference in hydraulic heads between the two parts, how fast the groundwater flow will be in your aquifer system. This is different methods where you can measure or determine your hydraulic activity of your aquifers. I'll skip it. Typical values, and then between the linking between the texture of your subsurface with the porosity, the hydraulic conductivity, and a specific yield. So next to the hydraulic conductivity, the piezometric head plays a role. So in your aquifer system, you often have wells installed where you can measure the head at the water level in the well, and that then determines the flow direction. If you have multiple wells and you compare the two, the water will of course flow from the locations with the higher piezometric head to the locations where the lower piezometric head is observed. Based on the Darcy's law, the equation of motions, and also the continuity equation, you can derive also for the groundwater flow system an equation that is then used in mathematical models to solve groundwater flow directions and amplitudes. So the groundwater flow modeling, so how is that generally done? So I will describe mainly the numerical groundwater models. There are also analytical models, but yeah, they are also often used, but in most cases, numerical models have higher capabilities of describing your system in more detail. So what you do is you divide your study area into grid cells. And every grid cell in the model domain, you will provide it with the parameters that describe your hydrogeological system. For the groundwater flow model, these are hydraulic conductivities that we just talked about, both in the horizontal and in the vertical direction. The porosity, effective porosity, is mainly of interest, the specific yield, and the specific storage, so the storativity terms. These parameters can be homogeneous or heterogeneous as you want. And the boundary can be determined by inactive cells. And then also in the vertical direction, you want to have your hydrogeology represented in your model. So you can have different layers representing your hydrogeological layers, so that both the aquifers and the aquithards can be defined in these numerical models. And then you solve this the groundwater flow equation. So this is the same equation as previously, but written in a slightly different manner. So for every grid cell, you will solve this equation and you will get a result. So a model that is often used for groundwater flow modeling is ModFlow. It's an open source model provided by the USGS. It's a modular model and it uses finite difference techniques. The most recent version is the ModFlow 6 version. So the fact that it is modular is quite interesting. So you have a basic package that does the calculation work, but then you can use all kind of submodules depending on how complex you want to make your models. So you have packages that describe your hydrological systems, so to describe your rivers or your wells or your groundwater recharge, evapotranspiration, as all your hydrological stresses. If you don't need some of these, you can just leave them out and the model will still work. And then you have other packages that deal with your numerical equations, for example, how you solve the equations, or how you do the discretization of your model, how you include the observations, and so on. Also here I have to be a little bit breaking the time. So the boundary conditions that we normally apply in this model are represented here. So what you can do, you have to define the starting values of your grid blocks, let's say. So this could be fixed potentials that you provide to the model. Groundwater recharge is also a boundary condition that you can provide. If you have wells, you have to specify how deep are the wells, how much water is taken from the wells, and where is the well screen. The river system is also something that drives your groundwater system. So you have to define the location of your rivers, the depth of the bottom of your river system, and also the water level of your system. And then the conductivity of the river system determines like how connected the river system is with the groundwater system. So how easily the water can flow from one in the other. Also, walls can be represented by the groundwater boundary conditions. So then I can skip this because I mostly explained there with the previous one. So the model scale that you use can be very diverse. You could use the whole catchment, let's say, as a model scale where you take the catchment boundaries as the boundary conditions of your model. It's quite handy, let's say, because then you can apply a no flow boundary and assume there is no groundwater crossing the catchment boundaries. But in most cases, especially for pollutant transport, you want to limit your model domain to make the simulation time reasonable, and then you will have to find a way of making a local model and finding good boundary conditions for this local model, which generally will be fixed heads that you will get from observation wells or from a regional model if you have one. So there is still a lot of different detail you can do. It depends on the model you want and the purpose of the model. Also the dimensions, so it can be, you can make a 1D model in ModFlow, you can make a 2D model, cross-sectional model, for example, in this way, or you can make a full 3D model, representing catchments, for example, and multiple layers. Everything is possible as long as you have the correct information. Also for the time domain, you can create steady state models, which I kind of give an average long-term condition of your groundwater system. And then you can also have transient models if one of the boundary conditions that you are using is dynamic in time. A typical dynamic in time boundary conditions could be the groundwater recharge, for example, but can also be the river head in your system, the pumping regime that you apply. Then you can make a transient model, and then you can also have a time series as an output. For a steady state model, you will have just maps with the groundwater system at one specific condition. Typical model output is the groundwater head as specified, so groundwater head in every simulation cell, and also groundwater flux and direction, which is indicated here with the arrows. So the direction and the velocity is here indicated with the color, and also the budget. The balance between water going in and out is returned. And then a nice application is the modpath. It is like the first step if you want to continue from the groundwater flow simulation to solid transport simulations, let's say. It's just using the output of the groundwater flow model, and it allows you to do some particle tracking. So you can specify grid cells and locations in grid cells as a starting point or ending point, and then let the model output determine where is the water, are these particle going to in the forward, backward, forward particle tracking, or where are they coming from in a backward particle tracking. I don't know if I think here I have an example. For example, for a groundwater well here that takes out a part of the groundwater in the system, you can specify the particles near the well, and then do a backward particle tracking, and then it will give you the capturing zone of the well. And if you, for example, know that you have a pollution somewhere in this capturing zone, then you have to be careful. For example, if the water in your well is going to be polluted. Okay, that was very brief on the groundwater flow modeling. Now we take the step to the solid transport model. So we built our flow model. We have our flow model output, so we know how the water in the groundwater system is moving. The variable that we need for our mass transport model is mainly the velocity of your water in the system. And then we add additional input, and then we can simulate how our pollutant is going to be transported. Typically, of course, we also use the source pathway receptor approach for this. Typical receptors in groundwater could be wells, rivers, wetlands, and maybe other aquifers that you don't want to pollute. Also similar what Ingeborg already taught previously, we have the transport equation, advection diffusion equation that we can solve here for the transport. There is no air phase in our system, so all the voids, all the pores are filled with water, but we also have dilution, similar as what you have in the unsaturated zone, an advection term driven by the velocity that is derived from our groundwater model. And then we could have sources or sinks of the concentration of our pollutant, and then chemical reactions are in fact very similar to what can occur in the unsaturated zone. So these are the same as dispersion diffusion is also, of course, an factor to take into account: absorption, decay, and chemical reactions if that is needed. So typically what we use for groundwater transport modeling is a solid transport model that we can link to our mod flow models. It's called the MT3D, the multi-species three-dimensional transport models. And it's recently, in fact, also replaced by the groundwater transport model. So that is what we can link to Modflow 6, to the new version. So it is a mass transport model potentially in 3D, but if your flow model is in 2D or 1D, it is also just linked to that version. And again, it is a modeler software. The typical inputs, as specified, you need a flow model first. So that is one of the inputs. And then you need to specify additional boundary conditions for the transport, which could be fixed concentrations, for example, in cells. Where is your pollutant entering the system? It could be a given concentration in a cell or somewhere, but you can also assume that the recharge that is entering your flow, your solid transport model has a certain concentration of a pollutant, or that there are infiltrating wells or infiltrating rivers that leach a certain pollutant in your system. You also need to model the initial. You need to specify to the model the initial concentrations. It could be all zero, but it could also start from a given concentration. And then the properties, the dispersion, dispersivities, the dispersion coefficient, absorption parameters, porosity, and dry soil density. So partly they are the same that what Ingeborg was using in the unsaturated zone models. And decay rates can also be specified. Maybe this one are all the packages that exist in Modflow on the solid transport model. So they describe a bit the input on what I just specified. I think I will go very quickly on them. You can just see them in the slides afterwards. And then some practical guidelines, maybe. We still have a couple of minutes. General requirements, model setup, model calibration. So what you basically do when you start modeling is following these steps. So first you have the model problem. What do you want to solve with your model? Do you have a certain pollution where you want to find a way of treating the system, or do you want to know how long it will take until a certain receptor is going to be polluted? You have to think carefully of what you want to do with your model. Then you want to gather the data that exists, hydrogeological data, and so on. You develop your conceptual model. How will you simplify the reality into your model? You select a code, a numerical setup. You assign the boundary conditions to your model, and then what is certainly always necessary for these kind of models are to calibrate your model very carefully. Yeah? So with some observations, model heads, for example, but also measured concentrations, you verify if the model is predicting what you are seeing in reality. So conceptual model size, and the size, what was said before, how big should your study area be? Do you need a 1D, a 2D, or 3D model? Of course, it's always the simpler you can make the model to solve your problems, the better, of course. Do you have to make your model steady state or transient? How many layers do you need? Which properties will you assign to the layers? What will you use as a boundary condition in your model? This is all things you have to decide on. So what data is generally required? So you need aerial imagery or a topographic map, preferably as a background for your spatial allocation, where if you want to specify where your pollution is happening or where your river is situated, you want to find that information in the background of your model. Hydrogeological data, of course, and the layers as detailed as you can find them. It will only improve the model a lot if you have information on where the different hydrogeological layers are occurring. If you have information on the conductivity, on the porosity of the typical layers, this you should certainly include that. You can get them from borehole logs, for example, or maps that exist. For the wells, of course, also if you know where the screen is, how much water is pumped in or out, this is something you have to take into account. Also, where rivers are, what the water level of the river is, how deep the river is. All the piezometric heads measurements in the system can help your model calibrating your model especially, and also groundwater quality data if you do a pollutant simulation. So the discretization typically, very rough between grid sizes then, could be between 1 kilometer by 1 kilometer, which is very coarse, to up to 1 meter by 1 meter, which is very small. Most often it is somewhere in between, let's say in the order of magnitudes of 10 meters by 10 meters for one grid size. Vertically, the discretization is based mainly on the hydrogeological layers, but if you want to do a solid transport model, it is good to make your layers as uniform as possible and maybe split the hydrogeological layers into smaller simulating layers, which are between 2 meters or 20 meters deep at the maximum scale. Some of the model types also allow for local refinements of the grid scale, so that can reduce the simulation time. Because especially the MT3D simulation, the solid transport simulation, they can really take a lot of time for one run. So for setting up the hydrogeology, you can do this in some graphical user interfaces, like for example, ModelMuse can help you with this. The top is mostly the topography, and then for the bottom layer, we choose like an impervious layer, which could be clay or an hard rock layer. And then you assign them with all the properties we have discussed before. So they have to be assigned a property. Also, if you have no idea, you should give a first estimate of, for example, your conductivity, porosity, and so on. And you can further update it in the calibration phase. Often there is also GIS data that can automatically be included in the models, like locations of rivers, well locations, catchment boundaries, and so on. And then the calibration of your model is a very important step, of course. You do a first simulation with your starting values for all the grid properties, and then it will the model will give you a hydraulic head for all locations, and hopefully at some locations you have a piezometric well, a monitoring well, and then you can verify what is my model prediction and what do I measure in reality. And you try to match the two as close as possible. And often, for example, hydraulic conductivity could be one parameters that you can change in time. Also, the storativity parameters to do the matching of these two. This can be done for the hydraulic for the flow model, but also for the solid transport model, where you need simulations of your or observations of the water quality of the parameters you are looking for, the solutes, and then you have a simulation versus observation, and then you can change the parameters until you reach a decent model. So the calibration can be done by trial and error, manually. It costs, of course, a lot of time, but you are in full control of what parameters you are changing. An alternative is to do automatic calibrations, for example, with the pest module. So in that case, you have to specify ranges in between certain parameters can vary, and the model will do multiple runs every time, check the observations with the simulations, change the parameter set until it reaches like an optimum parameter set. So that can be helpful to reduce the calibration time. Was a very small example that I had, but I think we are out of time. It's also just a very quick how does that look in reality, and what is the model output? So typically, this is contours of concentrations that you derive with your model results, and this is, for example, wells that you can pump and treat system that you can evaluate with your model. Okay. This was a very a speed course in modeling. I hope you were able to pick some things out.
Yeah, definitely, Jeff. No, thank you for keeping the speed in the presentation. No, I think it was very helpful to get an insight indeed on all the different aspects of the groundwater modeling. Also the importance of all the data you need. And of course, once again, your model is just as good as all the data input you made. I think that's clear. And indeed, the idea was to really have like an idea of what ground models can be. And I think you also showed the models that you have been using, which is also very interesting. So indeed, people can have a look at those afterwards as well. I'm just looking around in the chat or other if there are still any comments on your presentation or even on the presentation of Ingeborg. I didn't see anything popping
I can
up.
ask one if somebody has one, or I can ask one if nobody else does.
Yeah.
Hey, Jeff, can you give us just a practical example of maybe a project where you completed the modeling and then how that modeling may have been used in the field to, say, develop a remediation system or something of the sort?
Yeah, I didn't really include a practical example because sometimes it's sometimes very sensitive information, and not all clients want to have their data shown. But something that we do, for example, is in looking at some queries where they have a quite high concentration of metals, and they're still extracting materials from the quarry. And there are different strategies of where is the quarry can still be further excavated. And that's, for example, something we did. Like if you take more materials from that site, or you go deeper, what will then be the effect of the spreading of the pollution, and what is the best way that they can do their management of their system in order not to spread the metals.
That's interesting. So these are just natural metals in the rock.
There was a metal zinc company previously, and so they're natural materials, but the local area was polluted because of the factory that was historically there.
Yeah. Maybe to another question, Jeff, on that, I think maybe it's a difficult one, I know, but when I saw all the things you need to consider if you got a question, and let's say maybe a relative easy question, how many time do you need to foresee, for example, even if you only look at one solute at this perfect settlement to make up your whole model and this, can you give just a rough estimate, min, max? I know it's very difficult, but just to get an idea.
Yeah, but it's if you have to start from zero, let's say, so no flow model existing yet. You have to think in months, huh?
Yes, yeah.
at least, huh? So not not days.
No. That's what I was thinking of as well. And then it's just a basic concept. So
Yeah.
So they need a lot of information to get those things running. But okay. Okay, I don't see no more questions. So Jeff and Ingeborg, thank you once again for this really nice presentations for this last session. I think everybody is now open to go in the weekend. We see each other back on Monday at 10 o'clock. And I think from now on next week, we will have 2 sessions maximum a day. So looking really forward to having the next sessions. And thank you all once again, and have a nice weekend.
Very welcome. Thanks. Good luck.
Yeah. Okay. Thank you.
Bye-bye.
Bye.
Thank you. Bye.